My name is Owen, with me is Vladimir, and today we'd like to talk about some of the issues that you'll encounter and some of the solutions we have when you run NGINX and NGINX Plus instances in a cluster. Why might you want to do that? Well, a production deployment very rarely equals a single NGINX instance. In a production deployment, you care about fault tolerance. You run 2 or more instances for failover reasons and resilience. You may have issues with scalability. You might be anticipating very large volumes of traffic, very heavy SSL loads, in which case you may need more than one NGINX instance in order to handle typical traffic. So you need a multi-active cluster, multiple active instances. Or topology may require that you run several NGINX instances. You might be spanning several different clouds with GSLB. So by default, you need multiple instances there. You might be running in a Kubernetes environment with a daemon set configuration where the obvious way, the natural way to run NGINX is one instance per host. And you'll encounter 4 challenges as you deploy and manage and operate that cluster. The first 2 challenges we're not going to touch on our session today. They are largely solved. There's a large number of different ways you can deal with the issue of how do you manage configuration. You can roll your own solutions to push configuration out to NGINX nodes. You can select from the wealth of different configuration management tooling. You can use the Docker immutable container approach, or you can use NGINX controller as a central management point to push configuration out and sync it across NGINX instances. And similarly, monitoring is largely a solved problem in the sense that there's already a large industry there to help you solve that challenge. Companies like Datadog and New Relic and Dynatrace providing commercial solutions, open source solutions. Again, NGINX controller gives you a single point where you can pull metrics and logs and events to a single pane of glass and correlate sum or diff what is happening across your cluster. Today, we want to touch on 2 issues when you're running NGINX in a cluster. The first one, how do I distribute the traffic across my nodes? And secondly, how can I share runtime state? I shall talk to the traffic distribution challenges, and Vladimir shall talk to the runtime state. There's some really interesting tech in NGINX Plus that Vladimir was our lead engineer on, so he's going to give you some insights on how to scale NGINX in a runtime fashion. Let's look at distributing traffic first of all. The most common solution that we see, almost the de facto industry standard for software servers, is the Keepalived project. Keepalived is a daemon that runs on each individual NGINX instance. You can run it for other applications as well. You can provide high availability for services like MySQL, should you wish. So it's not tied to NGINX. Keepalived does a couple of things. The first thing it does is that it operates using VRRP to broadcast its own health and learn the health of the other peers within its little network. So it's a distributed system of understanding the health and state of the network. And secondly, it takes on the role of managing 1 or more virtual IP addresses, VIPs. These are floating IP addresses different to the permanent IP that you might assign to the NGINX machines. And when you configure Keepalived, you give it a set of VIPs that you wish to manage and a set of rules defined by priorities. And the job of Keepalived is to raise those VIPs on working NGINX instances, to monitor the health of those instances, and should one fail, re-raise any dropped VIPs on another instance. Here we have a snippet of the configuration file, so you can get a sense of how Keepalived operates. The priority is used in the rules to decide for each VIP which of the Keepalived instances should take priority to own that VIP. It unicasts to its peers to understand the health. The virtual IP address is the VIP that we're going to move about the cluster. The snippet I've shown you here is generated by a set of tooling that we provide with NGINX Plus. As a convenience, we provide a package that contains a tested build of Keepalived and some additional scripts to make it more convenient and easier for you to deploy it. If you were to use our package, you get these scripts with it. If you were to roll Keepalived yourself, you might want to build a check NGINX service script, as we have done, that, as well as checking that the host is up, also probes the local NGINX instance to make sure it's running, and a manual failover. This is another script that we've put in place so that you can touch a file in a well-known location, and that will mark that server as down. So it will drop its IPs, they'll be raised elsewhere, and that's useful if you want to take it temporarily out of rotation for a configuration update. And the notify script, which is used to maintain state as the state transition happens, to try and avoid some of the edge cases where Keepalived can lose state. Keepalived is simple, it's mature, it's very well understood, very well documented. You can customize it to work in a variety of environments. By default, it likes to use the local tools to raise and lower IP addresses. You can customize it using the notify script to talk to, for example, the AWS API to remap elastic IPs. And with Plus, we make it easier for you with a fully supported package that you can install and extend. The biggest weakness with Keepalived is that it doesn't support multi-active environments particularly well. It's possible to configure Keepalived to manage multiple IP addresses, to have passive instances as well as active instances, 3 or more instances in the cluster, but the configuration gets a bit complex. And if you want to have multiple active instances at the same time, they each have their own virtual IP address. The IP address is not shared by those instances, so you need either a downstream load balancer or round-robin DNS to distribute traffic to those destination IPs. So it's a great start, suitable for small deployments. In other situations, you might want to look at a couple of other approaches. IPVS, IP Virtual Server, operates in what's described as direct server return fashion, or triangulation. Each of the NGINX instances are manually configured to raise the virtual IP in local scope, so they don't advertise it. One of the instances then advertises it as the master, and it's configured with IPVS rules so that all the traffic comes into the master instance, and it forwards the ingress traffic, load balancing across the remaining itself and the other instances in the cluster. This is another configuration that's well supported by Keepalived. It takes on the task of publishing IPs with global scope, of setting up the IPVS rules to do the load balancing. So there's a good degree of flexibility here. The strengths are that this distributes connections across the cluster very efficiently. And there are additional load balancing rules that you can configure and weights that you can configure. With a little bit of care out of the box, you can manage it through Keepalived. The weaknesses are that it can be very complex to debug and troubleshoot should something go wrong. A lot of the tricks that it does with IPVS are hidden behind the scenes, and you need to work through and untangle the situation that it may have left your cluster in. Also, it has a degree of asymmetric traffic distribution in the sense that the ingress traffic is routed entirely to a single machine, the master, which then forwards that traffic back across the cluster. So that master typically has to handle twice the ingress bandwidth. That may be an issue for certain workloads. It may be absolutely fine for lighter workloads. The third solution that I'd like to run through quickly is similar to the IPVS solution. It allows you to take a single IP address and publish it on multiple NGINX instances, but it uses Multicast and the cluster IP module rather than IPVS. The mechanism behind this instance is that you raise the virtual IP on all of your instances, and you raise them with a common multicast address. That means that all incoming traffic is sent to all of the instances in the cluster. You then configure the cluster IP kernel module to drop all but your share of the traffic. The cluster IP module will hash incoming TCP connections, typically source IP and port, put those into a hash space, and then it is configured to take its share of that hash space. We'll run a quick demo. I'll show you how to set this up. I have a cluster with 4 NGINX instances. So let's just hit them so we can see them running. We're going to hit them with their private IPs first. So you can see they each give a slightly different response. We've got dev1, dev2. You can see the private IPs at the end, and 11, 12, 13, and 14. So we have 4 separate NGINX instances operating as load balancers, operating as web servers. Only 3 of them currently are configured to be in the multicast group and to use the cluster IP kernel module. So if I ping my multicast IP address, 40, you'll see we get 1 response and 2 dupes. So 3 instances are responding to the ping. If I try and grab traffic from those instances, so I'm going to connect to that .40 traffic IP, you'll see it runs connections. Most of the connections are picked up by 1, 2, or 3, but I've split the hash space into 4, and the 4th part of the hash space, nobody's listening on it. So roughly 1 in 4 connections at the moment are going to get dropped because we haven't configured the 4th machine in the cluster. I'll talk you through the configuration process. So at the bottom, I have a shell on dev4. That's our 4th machine. We're going to join the multicast group. We're going to set up our ARP so that we respond with the multicast IP when anyone ARPs for that IP address. And we're going to raise the IP address. And you'll see, if you look at the top, as soon as I raise the IP address, we now had 4 responses to the ping rather than 3. So we've successfully joined the multicast group and raised the multicast IP. Now, we still haven't set up the kernel module, so we're still hanging 1 request on 4. But if I then enable the cluster IP module, I'm going to assign it to traffic coming in on that IP address, the TCP protocol, so this won't affect our pings. And we're using hashing and source IP, source port. We have 4 nodes, and we are local node 4, so we're going to take share 4 out of 4. As soon as I do that, you can see from the top, we're away. So now the 4th server is responding just as quickly as the other 3. With these 4 commands, I've taken an unconfigured Linux instance, and I've joined the multicast group, raised the IP, and then set up it to filter so it receives its 4th part of the traffic. Strengths, again, distributes TCP connections across the cluster effectively. Typically simpler because there is not a single master. It's entirely peer-to-peer. Weaknesses, you need multicast. You may not always have an upstream switch that supports multicast. I'm running in VirtualBox on the laptop. Unfortunately, that does. The load balancing is not as rich. Failover, Pacemaker and Keepalived both provide options for failover for this technique. The cluster IP module has a kernel interface where you can push in the shares it should take or tell it to drop shares. So failover is achieved by moving shares across instances. However, if you're running an environment where you've got a sympathetic and supportive network team, you've got full control over the network hardware and its configuration. So you're not sitting in a virtual environment, you're not sitting probably in a colo, but you have your own data center. The gold standard for sharing traffic across instances will be to use ECMP, equal cost multipath routing. And an effective ECMP capable router will be able to perform health checks on the downstream or upstream servers and distribute traffic using algorithms like consistent hash to give you a better solution. So that was a whistle-stop tour of 3 or 4 different ways to share traffic within a cluster. I'd now like to hand across to Vladimir. And Vladimir's going to talk to us about how we can share state within a running cluster. Thank you.
Check. Microphone works?
Thank you.
Microphone.
Yeah, sorry.
Hello. So before we go into clustering, let's review what we have on a single node. What state do we have and how we share? As you probably know, Nginx has multiple worker processes. So we already have some method to share runtime state, but within a single instance. So the first thing that is actually shared is a configuration. How it is shared? The configuration is created by a master process, which reads it from a file on disk, and then master process creates worker processes. So each worker process has a same configuration. The thing we need to note here is that you cannot change this configuration in runtime because changes to configuration are not visible by other worker processes. If you need to change configuration for a worker process, you need to perform a reload. You send a signal to a master process, it reads new configuration from disk and starts new worker processes. So another thing that we have is an actual runtime state that allows us reading and writing some data that is shared between the processes. So what state do we have in Nginx? First thing we need to know is that we have connection limits and request limits. Usually it's just counters that count proper data. We have proxy cache metadata, where Nginx stores information about which objects were cached, its state, and where they're stored. We have status for upstream servers, fails, number of fails, various statistics for connections used for load balancing. We have shared SSL sessions cache, and we have a number of counters in stub status model. And we have even more in NGINX Plus. We have dynamically configured upstream servers that are shared between processes. We have health checks with their own status. We have sticky sessions to upstreams. We have a huge number of metrics in API module. We also have key value store, and we have HTTP session logs. So how do we share all this state? Nginx uses shared memory approach. What is shared memory? It's just a piece of memory that is visible for all processes that use it. First thing we need to note about this approach is that it requires an explicit configuration. Many of you, I think, can look into your nginx.conf file and find some zone references there. The zone defines actually a shared memory zone, a piece of memory of a finite size that will be shared by all processes that use it. Let me note some properties of this technique. The data access is effective because just memory reads and writes. Data is kept in a consistent state because all the processes that access it, they take log, modify data, and release log. Usually, you cannot avoid locking because data that is stored is complex. There are some cases when you can avoid locking, like incrementing some counters or if you are using some lockless algorithms, but generally you use locking to access shared memory. And the next thing we need to note that if a process crashes during using shared memory, data may be left in inconsistent state. And at this point, you have no chance, but you need to restart Nginx. You cannot continue working with the corrupted data. Hopefully, this doesn't happen very often, because a crashed process is a serious bug in Nginx. We will fix it immediately. So, can we go and extend this shared memory approach to the network? For example, right now we have a number of local processes that are accessing shared memory. Why can't we have more remote processes that will access shared memory using the same memory, using the same method? The short answer is no. Why? Because consistent access to data in network is expensive and complex. To respond to a request, each node must interact with some others. We can no longer respond quickly. We need to consult some other nodes. We need to ensure that all our cluster has the same data. And it's very hard to implement and configure it properly. For example, let's say we may have some master node that will help us with commits, but it will easily become a bottleneck because we installed our cluster with multiple nodes to scale. We are adding more nodes to handle more traffic. And if all this traffic will go to this master node, it will not work. And we can try to reduce number of nodes, and we can implement some clustering protocol that will try to use a majority of nodes. For example, we can use some complex logic with commits and transactions, but everything is very hard. There are a few people who understand how such protocols work, and there are even less people who can implement it properly. And there is another reason. The network nodes are ephemeral. Nowadays, we run a lot of our services in clouds, in clusters, in virtualization, with auto-scaling, and also network is not reliable. It can disappear. And remember what I was talking at the previous slide about a crashed node. If a chance to have a crashed process is not very big, the chance to have a networking node disappearing is much higher, and consequences are much worse in case of cluster, because it's not enough to restart a single node. You have to restart the whole cluster because you have no idea in which state your data is. So even if we go this way and implemented such approach, the result would be a distributed database. But Nginx is not a distributed database, and it's not going to be a database. If you really need a database in your project, just go ahead and use project you like, maybe integrate it with Nginx, because databases is just another beast. So what we want from an Nginx in a clustered environment? First thing we want to process input on each node separately. We don't want to make another network requests and load more nodes. Then we want to inform other nodes about our changes that we made locally. And next, we want to process new input with new knowledge. So if a new request arrives, we have some new configuration, we may process it with a new configuration. Can we implement something useful given these requirements? Of course, yes. The first thing we can do is configuration update. We just push some configuration update to the node, and it redistributed to the cluster. We also can perform session caching. A user is accepted on some local node, and it starts a session. It modifies it somehow, and meanwhile, we are transferring this session to other nodes. When a user will return, probably to some other node, it will be able to resume the session. Of course, it can happen that we were not fast enough to sync its session to our node. And what will happen in this case? In this case, user will just start a new session. It will be just a little performance decrease. And finally, we can apply resource limiting when our nodes will be aware of amount of data processed by other nodes. They can apply global resource limits. So right now, in NGINX Plus, we already have some models that implement these strategies. And in R15, we have added sticky session synchronization feature. And in R16, we added key value synchronization that can be used to manage configuration. And we have distributed request rate limiting, also in R16. Let me introduce the NGINX zone sync model, the core of our clustering solution. I name some properties of this model that will characterize it. And the first thing is it is a TCP-based stream model. It uses stream subsystem of Nginx for handling TCP connections, and we rely on operating system mechanisms to handle node state. If you have a live TCP connection to the node, we consider it live. If we drop TCP connection, then we need to start communicating with this node from scratch. It uses native Nginx asynchronous input-output. So in terms of resource usage, it is just handling one more client. It doesn't block Nginx. It's just like one of thousands of connections that Nginx handles regularly. From a topology point of view, we have a full mesh. Each node connects to each other to send them updates. And we support cluster nodes discovery via DNS. So nodes can publish themselves into DNS, and other nodes will know about this by making DNS requests. Internally, we have a very simple push protocol, and all the data that is floating between nodes is just modified objects that stored in shared memory zones with minimal framing. Our synchronization is based on objects. We are not syncing bytes, so we have objects with their properties. We can resolve conflicts, we can merge them. We offer full TLS support for inter-nodes connections, and we can configure latency or resource usage balance. Here is a simple example of cluster of 2 nodes and how NGINX zone sync model is integrated. We have 2 HTTP servers that using some models with 2 shared memory zones, foo and bar. So users are making requests to these models and have response. And we have zone sync model that from one side interacts with shared memory, and on the other side it uses TCP to communicate with the same modeler on another node. So here is a simple example of configuration of a load balancer that uses sticky sessions. We have upstream named backend with some servers, and it has sticky learn directive that uses shared memory zone named Z, its size 10 megabytes, and all requests that come to our server are proxy passed to that backend. How can we convert this into clustered configuration? First, we need a stream server block, and we say that this server will be handled by zone sync model. Next, we assign some IP address for this node, and we list nodes. Like in this example, we have just 2 nodes with specific IP addresses, and that's all. There's no some specific master nodes. You just run to NGINXs, and they start synchronizing their data automatically. And of course, we need to mark the zone to be syncable, just adding a sync flag. Of course, having your cluster configuration listed in a configuration file is not very interesting. We want to put it into DNS. So here is a little scheme that we have special domain name cluster example.com that holds IPs of all our nodes. And here is configuration we have right now, and what should we do to convert it into DNS? We just use a resolve flag and a domain name and a domain name server name, and we add a resolver to an NGINX so it could use DNS. Of course, you are running your cluster probably in some public cloud, or maybe you are not in control of your network connections. So we have full SSL support. The server part is very simple. It's just normal NGINX configuration. You add an SSL flag for the listen directive, and you configure certificates and everything that NGINX have. And for client connections, we have zone sync SSL prefix directives that are analogs of those you can find in a proxy model. So everything you have about SSL in NGINX is supported here, like certificate verification and so on. And this slide is a bit about tuning. The main thing we want to understand here is zone sync interval directive. It controls how frequently zone sync model inspects shared memory zone for changed objects. By default, it is set to 1 second. It may or may not suit your needs, because it depends on the nature of your data. You need to understand that we are synchronizing modified objects. A number of modified objects can never exceed the size of shared memory zone. For example, if a user comes and creates a session and then modifies it 20 times, you end up with an object, with single objects with some final state. So if you think that you need these intermediate states, you move the balance to more frequent checks. If you want to save some bandwidth, you may choose bigger sync interval. Also, we have some buffers directives that are similar to proxy. It's just about optimizing performance. So it depends on size of objects you are having in zone. And another interesting thing is zones in timeout. You may be interested. It controls the timeout, which says when to consider your node dead. So how much time you give for your node to respond. We have more modules that support synchronization, and their configuration is very simple. You just add a sync flag to the zone definition, and of course you need to have a stream block with your cluster defined. And that's all. Thank you.